So far, whatever we have covered is clear.
Yes, ma'am.
Any doubts in any topic?
I'm clear, ma'am.
Okay then. So we will resume from yesterday.
Good evening, ma'am.
Good evening. So we studied semaphores and how semaphore solves the problem of producer consumer, readers writers, and now we will look at how it deals with
Your voice is
the
not clear.
classical problem of synchronization. Not clear?
Yes.
Okay. Hello?
It is okay, ma'am.
Hello?
Okay, ma'am.
It is fine. Okay, okay. So today we would be discussing the classical problem of synchronization, which is known as dining philosopher's problem. Dining philosopher's problem. To begin with, let us understand what
Ma'am, we
the
did not
problem
receive
is.
your PDF, ma'am. Yesterday's class notes.
Yesterday's.
Yes.
Yeah, all right. I'll I'll give you now. One. So here. No problem. I think I have all of your email IDs. I will forward you.
Okay, ma'am. No problem.
Otherwise, I will send again to Samir. He will post in the WhatsApp group today's and
Okay,
yesterday's.
okay,
Okay,
ma'am. Thank you.
right. So uh, about the problem of dining philosophers, it's like there are five philosophers, and they spend their lives thinking and eating. There are five philosophers who spend their lives thinking and eating. What happens is that uh, these philosophers think, think and think. Later, when they get hungry, they eat. And the provision is that there is a circular table. There are five chairs surrounded. So here, in the center of the table, there is a bowl of rice. This is a rice ball.
Okay, ma'am.
And then there are five plates. For each philosopher, there is a plate.
Yes.
These are five plates. And there are five chopsticks laid on the table. Here are these five chopsticks. This, and here. Okay. Consider this one. This is philosopher 1, 2, 3, 4, 5. And then these are these chopsticks. They are numbered like 1, 2, 3, 4, and 5. When a philosopher gets hungry, philosopher needs two chopsticks, both the chopsticks, to eat. If any one of the chopsticks is not available, then he has to wait. And each one has two neighbors, left and right neighbors. If a philosopher uh, has to eat, then both the neighbors should not be eating, because philosopher requires two chopsticks to eat. If this philosopher, okay, students, please give me 1 minute.
Okay, ma'am.
Okay, sorry about that. Let us continue. So this philosopher needed two chopsticks, chopstick number 1 and 2 to eat. When this one can eat, when both left and right neighbors are not eating. Okay. What is the problem? The problem is that if this philosopher is willing to eat, then this philosopher should get both the chopsticks, and um, we have to ensure that whenever philosopher gets hungry, they should be only bounded waiting. Means philosopher should not be made to wait indefinitely for these chopsticks to be available. Consider that philosopher number 5 is eating with both the chopsticks and is not putting down. After eating, they have to put down the chopsticks on the table. Once they put down the chopstick on the table, the next philosopher can pick it up and can start eating. So when fifth philosopher put it down and second philosopher put the second chopstick down, then this philosopher number 1 can pick both the chopsticks up and start eating. You know that simultaneously they can't eat. This 1, 5 and 2 cannot eat simultaneously, because these resources are shared. These chopsticks are shared among 5 philosophers. Actually, you know something, uh, if there are 5 philosophers, you have to have 10 chopsticks. In that situation, no conflict will arise and there is no need to perform any synchronization and mutual exclusion and bounded waiting and those things. In this case, resources are fewer than the users. Now all these problems arises. um, Simultaneously, two adjacent philosophers cannot eat, and they whenever he get angry, he has to eat in a finite time. All these things arises because of the fewer resources. And in real world scenario and in computer system as well, you find fewer resources and more users. So this problem you can relate with computer systems resources and users. We know that resources are few and users are many. So um, there should be some mechanism to ensure that synchronization and mutual exclusion is preserved in this scenario. Then you can simulate this kind of solution in our computers related problems. Let us look at the solution. If you recall, a semaphore is an integer variable which has two operations, wait and signal. And you can create a semaphore that can be used between the cooperating processes in order to have synchronization effect. So here the solution is to have semaphores for chopstick. Wait, chopstick of I, where I represent the uh, chopstick number. We know that here in this case there are 5 chopsticks. Okay, so CS of I, and then weight chopstick of I plus 1 mod 5. So what does this means? Here uh, for this philosopher, he needs chopstick 1, this one, and chopstick 2. How to obtain this 2? You cannot here hard code the values, because this is a general case. A general case as in you can put any value of I and get the chopstick numbers. For that purpose, if I consider here philosopher 1, chopstick 1, and I is 1, here I is equal to 1, so I plus 1 means 2, mod 5 which is equal to 2. So 1 and 2 are required for philosopher number 1. If you put 3 in place of I equal to 3, then you need 3 and 3 plus 1, 4 mod 5 which is equal to 4. So for 3 it needs 3 and 4 chopsticks. So this way each philosopher is waiting whenever he gets hungry for both the chopsticks left and right, denoted by numbers, chopstick number 1 and chopstick number 2 here in this case, and generally it is chopstick number I and I plus 1 mod 5. All right, after that this if when a philosopher is waiting for both the chopstick, after a philosopher gets hey, oh hello, here when this philosopher is waiting, when the left philosopher and the right philosopher, means left chopstick and right chopstick, when both are available, when they get available, whenever signal is generated by this one and this one, if the signal is generated by both, then you can get this one can get it. Eat. If both are available, then the operation performed by philosopher is eat, and then after eating, once eating is done, then what he has to do? Send a signal to chopstick I and send a signal to chopstick I plus 1 mod 5. And then what happens after that? Thinking, because they spend their lives eating and thinking. Thinking they can do concurrently. There is no problem in that. Problem is with respect to eating, because to eat chopsticks are required, and chopsticks are fewer than uh, the required number. Is this okay? So whenever a signal is generated, another philosopher, this is for one, another will have the same set of lines, another one will have again weight cs of I and weight cs of I plus 1 mod 5. Hmm? It and signal. What happened whenever one process has started waiting and another send a signal, then it comes out of wait and can enter to the next line. And even if the other the other one also issues a signal, then this wait operation is done, and then the one which is waiting can uh, begin eating. This is also like this, same code. And whenever after this process eats, this process can send a signal, and then the one, if this one is waiting, will stop waiting and go to the next line. So how this semaphore is providing a solution to this dining philosopher problem? We need to represent each chopstick by a semaphore, and then the philosopher grabs a chopstick by executing a wait operation and releases the chopstick by executing a signal operation. Signal is like releasing, all right? And then this shared data, what is the shared data? This chopstick I plus 1, I plus 2. It's like chopstick 5. I have to declare like chopstick 5. And initially all the elements are initialized to 1. This solution, semaphore solution, guarantees that no two adjacent philosophers are eating simultaneously. Means no two neighbors are eating simultaneously. However, it has the problem of creating a deadlock. When deadlock occurs and how deadlock occurs in this solution, let us look at here. Initially, every chopstick CS of 5, so it is CS of 1, 2, 3, 4, and 5. Okay, so all 5 chopsticks are initialized to 1. Suppose that this this one picks up this chopstick and issues a weight on this one, and this one picks this and issues a weight. This one picks up this and issues a weight. Likewise, 4 and 5 as well. What problem occurs in this scenario? Problem is that each one has picked his left chopstick and waiting for the right chopstick to be released, and everyone is doing the same. Okay, 1 to 5 all are holding one and waiting for another, and this is continued forever, and therefore it creates a situation of deadlock in which no one is able to proceed. All right, moving ahead to the next concept, which is monitor. Semaphore is just a integer variable, whereas monitor is a collection of variables as well as the functions that implements the operations. Monitor is represented like this. Here you have shared data, and these are operations, and here you have some initialization code. In semaphore, because it is just a variable I, S, or chopstick CS, or producer, consumer, we saw WRT, M. These are just variables. And then what happened? Any process can access these variables. The problem that it is creating is that there is no defined procedure for accessing these variables. Monitors overcomes that problem and creates a structure which combines both the variables and the functions. And then what happens now? These variables can be accessed only by these functions, not by anyone else. And if there are processes that are waiting, they have to form a queue. They cannot enter. Once a process is inside this monitor, another process cannot enter until the first process comes out of it. If another one is waiting, they have to wait outside, means they cannot do any sort of modifications on this shared data. All right, and then the advantage of monitor is that it ensures that only one process at a time can be active within the monitor. Whatever I said just a while ago is essentially the advantage of the monitor. Only one process is in a monitor at a time. And a programmer can create condition further, can add conditions that when satisfied allows the process to execute. For that, programmer can create a monitor condition variable inside a monitor. So condition x comma y, some sort of condition on x and y, and the operations which can be called on these conditions are same: signal and wait and signal. We can have x dot wait, y dot wait, x dot signal, y dot signal, like we had for semaphore. Similarly, we can have for monitor in the form of a condition variable, which is also a part of monitor. So that cannot be invoked directly. It has to be invoked by the functions. And the solution to deep PP, which is dining philosopher problem, provided by monitor, is essentially like this: dp dot pickup of I, eat, and dp dot put down of I. If you observe here, this pickup and put down are not variables, rather they are functions. And apparently variables are passed as arguments to these functions. If we further try to get details on pickup, so what happens in pickup? The logic for pickup would be like this: you have a pickup function. When a pickup function is activated, when the state of the calling philosopher is equal to hungry, and if the one who is calling is hungry, then he has to check the neighbors, check the neighbors. That is by calling test. What is there in test? Let us look at what is there in test. In test we have test of int I if state of I plus 4 mod 5 is not equal to eating, and state of I plus 1 mod 5 is not equal to eating. This is like confirming both the neighbors are not eating. Okay, I plus 1, if I is 2, who are the neighbors of 2? You see in this illustration, for I equal to 2, the neighbors are 1. The neighbors are 3 and 1. Let us test whether we are getting 3 and 1 for this equation. When you have I equal to 2 and you substitute 2 plus 4 mod 5, which is equal to 6 mod 5, 1. The remainder will be 1. So 1 is one neighbor, and I plus 1 means 2 plus 1 is 3. 3 mod 5 is 3. 3 and 1 are the neighbors for I. All right, like this, the one who gets hungry first test whether both the neighbors are not eating. When both the neighbors are not eating, only then he can set his state to eating, and then he can send a signal to himself. All right, this is testing. After testing, consider that both the neighbors are not eating. When both the neighbors are not eating, here, if the state of I is not equal to eating, what does this means? Here, when test fails means anyone is eating or both are eating. In that state, in that situation, what happens is, if state of I, then what happens here? State of I will not be equal to eating. When both are not eating, then only I is eating. Okay, when both I plus 4 mod 5 and I plus 1 mod 5 are not eating, then I is eating. If state of I is not equal to eating, what does this implies? it essentially means that any one or both are eating. So that time what it has to do? It has to wait. Self of I dot wait. All right. This is about pickup. And then after, if pickup succeeds, when pickup will succeed? When both are not eating, neighbors. Then it says that it is eating. And then it can enter eat state. After eating, uh, put down function has to be called. What is there in put down? In put down, has philosopher has to change his state to thinking. Here you can see here state of I equal to eating. When he gets hungry and when both the neighbors are not eating, his state is eating. Here when it is putting down the chopstick, he changes his state to thinking. And then uh, he, he tests whether any one of the uh, neighbor is waiting, and it's like sending a signal to if any one of them is um, waiting, then signal will be sent to them, so that at least they so that by then they can start eating, because now I has gone into the thinking state. This is the deadlock free solution provided by monitors for dining philosophers problem. Any doubt in this? I'm going ahead with the new topic. So if you have anything to ask, you can ask.
No, ma'am.
Fine? Okay.
Yes.
Then I am moving on to the next topic, which is deadlocks. A deadlock can be explained with the help of an analogy. Let us look at this. A crossroad. One vehicle here, one vehicle is coming from here, one vehicle is coming from this side, another one is coming from this side, and another one is coming from this side. Okay, these are four vehicles. They all of them got stuck at this crossroad. 1, 2, 3, 4. Sometimes you can uh, find this type of situation even in our real world, where people will say you go first, or you move behind, we will go first. Okay, there are very few who say I will wait, you go first, but then the general scenario is that this one will tell 4 to move, 4 will tell 3 to move, 3 will tell 2 to move, 2 will tell 1 to move, and this cycle continues. So it is like they they are in a situation of deadlock, and this situation will not change until any one of them uh, just move behind. In uh, taking this now to computers, what happens is processes P1, P2, P3, P4. Consider there are four processes, and there are few resources which are held by these processes. Consider that P1 holds resource 1 and requesting for resource 2, which is held up by P2, and this P1 is holding R1 and waiting for R2, P2 is holding R2 and waiting for R3. P3 is waiting for R3 and P3 is holding R3, waiting for R4. P4 is holding R4, waiting for R1. And look at this, they are in cycle. This is a cycle. Therefore, this kind of situation is called a deadlock. And no process can change their state because they are waiting for the resources which are held up by other waiting processes. All right. Next, uh, the system model with respect to deadlock, we find that in a system we have finite number of resources. We have resources which are finite in number, and they have to be distributed among the number of competing processes. Processes are competing for the resources, and there are several types of resources like memory space, CPU processors, files, IO devices, and so on. And there are physical resources like printers, um, hard drives, and there are logical resources like files. And what happens is a process can request for a resource, use a resource, and release a resource. Here, process request and then use it within itself, and then release. Request for the resource, use the resource, and release the resource. This is the system model. Now, what are the characteristics of deadlock? When it occurs, why it occurs, what are the conditions that state that the situation or condition is in deadlock? So there are uh, four necessary conditions for the deadlock. Deadlock characterization. Deadlock situation will arise if the four conditions hold simultaneously in any system. What are the four conditions? Mutual exclusion, hold and wait, no preemption, circular wait. These are the four conditions. When they are true simultaneously in any system, deadlock condition arises. What is mutual exclusion? Mutual exclusion says that a resource is held only by one process at a time. Right? A resource is held by only one process at a time. We know that mutual exclusion means a resource can be accessed by only one process at a time. Okay, exclusive access is mutual. When this occurs, and then hold and wait is a condition in which process holds a resource and waits for uh, another resource, an additional resource to be acquired by it. Okay, let me give you here. There are two processes, P1 and P2, and there is a resource R1. In mutual exclusive access, if P1 is holding this R1, P2 cannot get access to R1. Okay, hold and wait means what? There are two processes, P1 and P2. P1 has R1 and P2 has R2, and P1 is now waiting for R2, and it is holding R1 and waiting for R2, and P2 is holding R2 and waiting for R1. Hold and wait. Non-preemption, no preemption implies that a resource is released voluntarily by a process, not forcibly. Voluntarily in the sense that P1 now is holding R1. If suppose P1 is intending to hold R1 for 2 days, then no one will say anything to P1. P1 can have the access or right of R1 until P1 desires. Only when P1 feels that okay, now I don't need R1, I should release it. Only that in that situation, P1 will release R1. No preemption occurs when a resource can be released voluntarily by a process. Okay, not by the system. All right. That is no preemption. So it is about voluntarily release of resource. Circular wait. Circular wait is the same thing which I already told you. P1 waiting for P2 to release, P2 is waiting for P3 to release, P3 is waiting for P4 to release, and P4 in turn waiting for P1, thus forming a cycle. This is circular wait. All right. Moving ahead, there is a visual representation known as resource allocation graph, which is a directed graph uh, that can model the deadlock existence or non-existence, whether deadlock is there or not there. Okay, we can find out from a graph known as resource allocation graph. Resource allocation graph, in short RAG. This graph has two types of vertices and two types of edges. Vertices are processes are represented by circles, and resources are denoted by rectangles. Example P1, and this one example is R1. And here another important aspect of resource is that in a system you may find a single instance of a resource or multiple instances of a resource. You can have uh, two files which are almost similar, okay, identical. In true sense they are identical. You can say that there are two instances of that resource, or you can have a single instance of a resource, say a printer. This one about vertices, and then you have edges. Edges again are of two types. Request edge, it is a directed line from process to resource. For instance, PI to RI, process to resource. That is, PI is requesting for RI. Another one is assignment. Assignment is a directed edge from resource to process that denote that the resource has been allocated to this process. Okay, when a particular resource is allocated to a process, then it is assignment. An illustration for this is here. You have R1 with single instance, R3 with single instance. There are processes P3, P2, and P1. And then here we have other resources. R3, R3 is here, R2 and R4. Here I am drawing. Okay, I will use different color. Pink circles denote processes. Blue rectangles denote um, resources, and green edge denotes a request edge. Green line denotes a request edge. P1 is requesting for R1, and P2 is requesting for R3, and P and this purple will denote the assignment edge. R1 is assigned to P2, and R3 is assigned to P3, and one instance of R2 is assigned to P2, and another instance of R2 is assigned to P1. Look at this. This is an example of resource allocation graph. In this graph, there are three processes P1, P2, P3. There are four resources R1, R2, R3, R4, and there are two instances of R2 and three instances of R4, and resources are requested. Uh, you know, P1 is requesting for R1 and P2 is requesting for R3, and assignment. R1 is assigned to P2 and R3 is assigned to P3, and R2 assigned to P1 and P2 because R2 has two instances which can be assigned to two different processes. In case there is a cycle in this RAG, then it is said that there is a deadlock. If there is no cycle in this graph, there is no deadlock. Let us look at whether we have a cycle in this or not. Here P1 to P2, P1 through R1 to P2, through R3 to P3, and then R2 to P2 and P1. There is no cycle, which signifies that there is no deadlock here. All right. You can modify this a bit, or I can another one. I can take a smaller one. We have R1, we have R3, single instances, and we have R2. Here R2, and here R4, and we have processes P1, P2, and then P1 is requesting for R1. R1 is assigned to P2. P2 is requesting for R2, which is assigned to P1. Okay, these two are not required, or you can have another one also. You can create another cycle as well. So you can see here there is a cycle starting from P1. Again, we are reaching back to P1. This indicates that there is a deadlock. All right, next. uh, consider that there is a deadlock. Whenever you find a cycle in this RAG, which signifies that there is a presence of deadlock. When deadlock is there in the system has to deal with the deadlock. So what are the methods for handling the deadlock? Uh, Going ahead with the methods for handling deadlocks. Methods for handling. There are essentially three methods to handle the deadlock. It's like one of the three ways can be used. The first one is to prevent deadlock. Second one is to uh, um, detect and recover from deadlock. Detect and recover from deadlock. Third one is ignore that problem of deadlock altogether and pretend that there is no deadlock. Okay, ignore DL. Let us look at the first method, which is prevention, deadlock prevention. Deadlock prevention, these in, uh, this method includes set of approaches for ensuring that at least one of the necessary conditions do not hold in the system. We know that if four conditions hold um, at the same time in a system, apparently that is deadlock. What deadlock prevention method does is that it ensures that at least one of the necessary condition cannot hold. When at least one cannot hold, it means that deadlock may not occur, because for deadlock four conditions are essential. So let us look at how. Okay, please give me a minute. Okay, students. Okay. So we are here trying to understand the deadlock prevention set of methods. So what is the first necessary condition? Does anyone remember first necessary condition?
Consists of resources.
And no, deadlock, in deadlock characteristics we studied four conditions.
Mutual exclusion.
Very mutual exclusion is the first one. Let us see whether we can ensure that this condition do not hold. Mutual exclusion. What is mutual exclusion? That a resource is uh, used in a non-shareable manner. A resource cannot be shared. That is all about mutual exclusion. Can we avoid mutual exclusion? Can we make a resource to be shared by multiple processes? Here the goal is to prevent a deadlock by ensuring that any one of these necessary conditions do not hold. So, apparently mutual exclusion means use in non-shareable mode. There are resources which cannot be made to uh, cannot be made to be available for multiple processes. You cannot make a resource available for multiple processes in a sharing mode to be used by them. There are few resources like that. In readers writers problem, we studied that when a writer is writing, no other reader or writer can access the resource. That is absolutely in non-shareable mode. Therefore, whenever a resource is shareable, it will be in read-only mode. If it is in read-only mode, it can be shareable. Otherwise, it cannot be shareable. And thus, deadlock cannot be prevented by denying a mutual exclusion condition. This is essential to have. When for read-only, we may not have. We can share. But for other tasks, for write, for update, it must be in non-shareable state. You cannot have a resource. Therefore, this mutual exclusion uh, cannot be denied. This must be there. Now, moving ahead to the next one, which is what is the second condition?
Hold and
Second,
wait.
hold and wait. Very good. So, hold and wait can we make sure that a process who is holding a resource cannot wait for other resources. That is the idea here. Here we ensure that whenever a process requests a resource, it does not hold any other resource. Then what happens is a process has to determine uh, its resource requirements in advance. If P1 requires R1, R2 and R3, then P1 has to uh, request for all the three before it begins its execution. Well, in this scenario, what happens is P1 will not hold and wait because it has the requested and needed resources available to it, available at its disposal even before its execution. Okay, this is one way. Another way is that P1 requires R1, R2 and R3. So what P1 does is initially request for R1 and R2, and finish up the work with R1 and R2, release R1 and R2, then request for R3. This is another way of ensuring that this does not occur, hold and wait. And no preemption is about, no preemption means it ensures that the process does not hold back the resource um, till it wishes. It has to release it. When it has to release, um, for that, a protocol may be followed. A protocol like if a process is holding a resource and uh, waiting for some other resource, then probably system forcibly revoke resource 1 from P1. If P1 requires both at the same time, then P1 has to start all over again, requesting R1 and R2 again, and so on. And uh, here, if P1 requests holds R1, no, another case. Let us take another case. P2. P2 is holding R2 and R3 and requires R4. Okay, and requires R4. Then what P2 has to do? If R4 is not available right away, P2 has to release R2 and R3. It is, made mandatory by the system. The system revoke these two resources. Okay. Therefore, what is happening here? There is a preemption. There is a preemption. Preemption means what? Revoking, taking back the resources, and it is not leaving at the wish of the process. And we can have this kind of scenario where we can um, we can ensure that the system ensures that no preemption does not hold. The last one is circular wait. When circular wait happens, what can be done is that there is a policy here. The policy is all the resources have been given numbers, and this hard disk given number 1, and CD drive given number 2. No, CD drive given number 1, hard disk number 2, and then um, what else, printer number 3, like that. And then a process has to request for a resource in the increasing order. A process can request for CD first, then can request for hard disk, then can request for printer. Likewise, it can request in the increasing order of the IDs given to these resources. This is one way to not have circular wait in the system. And second way is that whenever process requests, first way is request in increasing order. Request for a process in increasing order. Second is to request in such a in a suppose a process does not follow this increasing order and request for a resource uh, which are having lesser than this, then what it has to do, it has to release the resource that it is holding and can acquire the requesting resource. So when the idea of requesting the idea of holding is greater than requesting, then what has to be done? It has to release and acquire the another one. Okay, this is deadlock prevention techniques. Any doubt in these things?
No, ma'am.
Okay, then let me proceed with the next method, which is deadlock avoidance. Deadlock avoidance. Deadlock avoidance is concerned with not creating a deadlock situation in the system. It's like you try to avoid something altogether. So essentially, it is like um, taking precautions so that deadlock does not occur. For this to happen, a process has to give the uh, resource requirements in advance. Okay, here the point is process has to specify in advance its resource requirements. Then what the system does is system um, have this information. A system maintains this information. Which information? uh, the resource requirement information system maintains, um, and then system will see that the process who is being assigned the resource is done in such a manner that eventually there is no deadlock. This we can नहीं. Okay, so in this, let me illustrate this with an example. Uh, Before that, try to understand what a safe state is. Okay, let me give you an analogy so that we get to understand this. Suppose, uh, suppose a father has 100 rupees. Okay, and this father has okay, if not father, some person. Okay, person P has 100 rupees, and this person has to and the person is receiving the request from children. So consider that this person gives some amount to the children. One will say, C1 will say that I need instead of rupees, let me take something which is reusable. Okay, toys. This person has toys. Say that this person has toys. How many toys are there? 10 toys are there. And then C1 is requesting for 3 toys. C2 is requesting for 7 toys. C3 is requesting for 1 toy, and C4 is requesting for 8 toys. Okay. Then what P1, what P can do is if 3 toys are given to C1, then how many toys will be left here? 7. Then
7.
yeah, 7. Then system will check which child's request can be processed in these 7. Based on that, this person will decide this toy should be given to which child. Okay. So first child 1 has come and took 3 toys. Now child 2 said that I need 7, child 3 said I need 1, and child 4 said I need 8. What this person will do? This person will see that it has 7 toys. These 7 toys can satisfy the request of C2, C2 and C3, but not C4. Right?
Yes.
When P can satisfy the request of C4, if C1 returns, it's like they have to return back. They have to play and they have to return. Once C1 returns, then P can assign 8 from 10 to C4. All right. So what happens now? C1 got 3. C2 can be given 7. Okay. There is no problem in that. After some time, C1 returns 3. All the 3 C1 returns. Now how many toys this person has? 3. Now person will check these 3 toys whose request can be satisfied. C3 request can be satisfied with only a single toy, because its requirement is 1 and available is 3. So from 3, 1 can be given to C3. So 1 is given to C3. Okay, here 1 is given, here 3 was given, here 7 was given. Later, after some time, C2 returns 7. Okay, returns 7, and P1 has got now 2 plus 7 is equal to 9, because 1 just it has assigned it to C3. Okay, so from 3, 1 was assigned, so 2 were remaining. 2 plus, now we got 7 from C2, so 2 plus 7 is 9. So now P can assign this to C4. How many? Out of 9, 8 can be given to C4, and then P will have still 1, and there is no situation of deadlock. All requests have been satisfied, but it may not be in the same order. All right.
Yes.
It may be in different order. Eventually, all requests are satisfied without any deadlock situation. This is the whole idea of this deadlock avoidance, and safe state. Having a safe state. Having a safe state is it determines that if I assign resources to processes, whether this will lead to a situation where there is no deadlock. When there is no deadlock, it is a safe state, and it has to find a safe sequence. In order to reach safe state is that there is no deadlock, and to reach safe state is it has to determine safe sequence, means in which sequence resources should be allocated to processes. All right, let us look at this with an example. Okay, safe sequence is the mm, series of or sequence of processes resource assignment to processes, series of resource assignment to processes uh, that does not lead to deadlock. That there is no deadlock. Okay. Let us look at an illustration example. A system has resources which are different types. Um, no, a system can have resources of different types. In this example, let us take only one, which is the hard disks, okay, which are uh, hard disk. Which one is appropriate? There are 12 printers. Let us take printers, and there are three processes: P0, P1, P2, and their maximum needs. How many printers they need? P2 needs 10, P1 needs 4, and P2 needs 9. And what are their current needs? Current need is 5, 2, and 2. All right. And now what we have to determine? We have to determine the safe sequence, because that safe sequence will lead to the safe state. How to determine that safe sequence? Here we can go for allotment. Out of 12, yeah, out of 12, there are 12, no? Out of 12, out of 12, suppose 5 has been allocated to P not 5. So 12 minus 5, how many are remaining? There are 7 remaining. Out of 7, if 2 are allocated to P1, then 7 minus 2, which is equal to 5. Okay. And then out of 5, if 2 are allocated to this P2, then we get 3. We will have 3 resources left over. And if you compare this, their maximum needs and how many have been allocated, then what further what they need more remaining need is here 5. This is 10 minus 5 is 5. This is 5 remaining, and this is 2, this is 7. Now tell me, system should have how many? 3. What system should do? To which process system should allot next? First it has allotted to P0 and P1 and P2, 5, 2 and 2. Now their remaining needs are 5, 2 and 7, and leftover resources are 3. Now what system has to do? To which process system should allocate those 3?
Current needs.
To which process? P0, P1 or P2? To which process?
P0.
From this P0, if we allocate 3 to P0, okay, So suppose now 3 is allocated to P naught. Consider this case where you are allocating 3 to P naught. When you allocate 3 to P naught, what will be the remaining need of P naught? 2. And here you will get 1. 3 minus 2 is
1.
3 minus 2 is 1. So what is the leftover resource? 1. Hmm? There are only one resource. There is only one resource. And what are the needs? Needs are
P1.
that 2, 2 and 7. Can you satisfy any process need from this one?
P1.
How? Okay, okay, right, P1. So suppose if you give 1 to this P1, still P1 needs 1. P naught needs 2, P1 needs 1, and P2 needs 7, and this is 1 minus 1 is 0. Now there are
Madam,
no resources.
uh,
Now,
we can share P01, P1 is 1, P2 is 1. We are having 3. And
mhm.
in current needs, at least, uh, for P2 is needed 2, but we are having, if we give 1 means it will be only 1. And if P1, and that, which means for each one we will be providing. We are
Hmm.
having 3 resources, and the current needs are for P0 is 5. If
Hmm.
we give for 1, the current need is 4 for P0.
Hmm.
And for P1, the current need is 2.
Hmm.
If we provide 1 means only 1 is the current need for P1.
Hmm.
And for P2 is also in the same manner.
But
So that
no one is completing. No. Look at here. There are no resources left, and
yes.
no process has completed. So is this a safe state?
Mm,
It is not a safe state. What is a safe state? And look at here. It is like deadlock situation. Not
P1
like it is a
P1 is
deadlock
2.
situation. Hmm?
P1 will be completing, madam. Then
When right,
if
you are
we,
coming
P,
to, yeah, you are coming to correct right sequence now. Tell me. So
for
now,
P1, if we give only 2,
yes, very good.
1 is
So
remaining.
very good. So here we will cancel this up because
Yes.
this will not lead to safe state. So I am canceling this. This one is cancelled, this part, and this part is cancelled because this is not leading to a safe state,
That,
and the sequence is also not a safe
that,
sequence. Now we are here. Now you tell me what to do.
first go for P1.
Very good. So
Uh,
first assign to P1. How much? 2.
2,
When you assign 2 to P1, so this will be 4. Okay,
4.
and here 3 minus 2 is equal to 1. Here 1 will be there and P1 has 4. What P1 will do? Use the 4 resources and then release it, because a process will request use and release. So now P1 has released 4. When P1 has released 4, this is given back. When it is given back, it is added. 1 plus 4 is equal to
5.
5. Now the system has 5. Now, to which process we should allocate 5?
P naught.
Very good. Now 5 is allocated to P naught. And then here we have 5 minus 5, which is equal to 0. And here uh, P naught has got 10, 5 plus 5, 10. And this 10 it has used and it has now released. Okay. So after P naught released, system got 10.
10. Then we go for P2, which is required of 2.
Yes. Then we go for
P2.
P2. P2 needs
2.
7. No, 7
Oh,
here remaining.
okay, 7.
Remaining 7. So you allot 7. So minus 7, which is equal to 3.
3.
3 is left. This is 7 plus 2. 2 already there. 2 plus 7 is equal to 9. So
9.
totally now it got 9.
9.
Okay, now it has used 9 and it has released it. So
Yes.
3 plus 9 is equal to 12. And
12.
here P2. This is a safe sequence. And look at here, there is no deadlock. First P1 has completed, then P0 has completed, finally P2 has completed. And all have completed without creating any deadlock situation.
Okay.
Do you understand, all of you, this one?
Yes, ma'am.
Yes, ma'am.
Yeah, right. Good. Next, uh, to perform all this, the algorithm is uh, uh, defined, which is known as Banker's algorithm. Banker's algorithm. Banker's algorithm has got its name from the banking system, where uh, it is practiced that no customer will request for the amount beyond the limit. Every customer has been given a limit. Beyond the limit, no customer can request, and a bank also will never allocate its available cash to one single customer so that it cannot fulfill the requests of other customers. That policy which is being followed in banking system has been adopted here, and that concept is given in the form of an algorithm known as Banker's algorithm. All right. What happens in this is, whenever a new process enters the system, same thing, it has to declare maximum number of instances it needs. Look at here, this is maximum needs. It has to specify, and the maximum need must not exceed the available resources. P naught cannot say that it needs 15. If it says 15, no matter what sequence is being followed, no matter the allocation order, it will never lead to a correct state, because we cannot its request cannot be satisfied by the system. All right. So the condition is that a process cannot specify its maximum needs more than the available resources in the system, and the system determines in which order resources need to be allocated to processes based on the availability, just what we looked at. Okay, it has, how it has created this. It has not followed the sequence p0, p1, p2. It has allocated resources left over to p0 first, and p0 has completed before sorry, p1 has completed before p0 and p2, ensuring that there is no deadlock. Okay.
Yes, ma'am.
And this Banker's algorithm has obtained its name from banking system, and it will never allocate all of its resources um, to a single process. And process must specify the maximum needs. And the implementation of Banker's algorithm is that it requires a few data structures, which are used in Banker algorithms. They are available. Available is a structure. What we saw, just an illustration, we had seen that available indicate the total number of resources that are available. And then there is another data structure which is maximum. Maximum is that the maximum needs of a resource by a process. Allocation, this one holds information about which resource has been allocated to which process. It's like this: max of ij, allocation of ij, where the process I no process I here process I maximum resources j, okay, process pi and its maximum need in the form of this rj, resources j, and allocation process pi getting resources j. And then need is a structure that maintains the information about what the remaining resource needs of each process. All right. And then this banker's algorithm comprises of um, further two algorithms: safety algorithm and resource request algorithm. All right. Okay. This banker's algorithm comprises of safety algorithm and resource request algorithm. What a safety algorithm does is it finds out uh, whether a system is in safe state or not. This safety algorithm determines whether a system is in safe state or not. System is in safe state or not. Resource request algorithm is concerned with allocating receiving the request of a resource by a process, and then ensuring that whether the allocation leads to a safe state. All right. So then there is a numerical example. Mm, I think if I start now, I can't cover. So I will be discussing the numerical example, and its a numerical example for bankers algorithm is pretty important, so you need to know that. And today please go through safety algorithm and resource request algorithm, and then tomorrow we'll look at an illustration, a numerical example. Okay, any doubts in whatever we have done so far?
No, ma'am.
No, ma'am.
Okay, I think Varaprasad, you asked me about these PDFs, right?
Yes, ma'am.
Okay, can you send me your just ping me on WhatsApp?
Ma'am?
Do you have my what number, WhatsApp number?
No, ma'am.
No. Okay, then uh, okay, I'll send to Samir. Okay, this
Ma'am,
hmm.
Not there, ma'am.
Samir is not available from last day also.
Then somebody if you have my WhatsApp number, ping me, I will send to you.
Yes, I'll ping you, ma'am.
Now only you ping me, now only I'll send you.
Yes. Now, okay. Now
What is
I'll
your
send
name?
you the.
Jyoti.
Yes,
Okay,
ma'am.
Jyoti, please ping me on WhatsApp so that I can share what all I have to share this
Okay.
Uh,
today's
I think
today's the recording
recording
and
of
the notes.
recording I posted in the YouTube.
The first
That play,
days.
yeah, in that playlist only you will find all the videos from now onwards.
Okay, ma'am. And a small request. In the class, you have given some questions. It's of
Right.
one. Can you please share that also?
Yeah, I'll share that also with you now. Uh,
Okay.
and please hold on.
I'll ping you on WhatsApp now only. 1 second, ma'am.
Okay, Jyoti.
Yes, ma'am.
After I share with you the question bank, the here this deadlock, deadlock. Today's is deadlock one. Tomorrow will be deadlock two. I think file system interface and file system implementation one.
Yes,
Yes,
ma'am.
ma'am.
Yeah, you have only first two files.
Yes, yes.
Yes, ma'am.
So I have to send four now. One,
Yes, ma'am.
two, three, four, four. These four I will send plus question back. And video I already yesterday. I think straight away I posted after the class.
Yes, ma'am.
Okay. So in that playlist only you will find it.
Okay.
All the
Okay,
videos.
ma'am.
You have that playlist, right?
Yes, ma'am.
I'll check, ma'am.
You
Actually,
share
I'm
once.
not having.
You share the ones.
Okay, I'll share that again to Jyoti. Jyoti, please post everything in the WhatsApp group so that everyone can get this.
Sure, ma'am.
Okay, students, then see you tomorrow.
Thank you, ma'am.
Okay, thank you, ma'am.
Bye bye.
Bye. Bye.
Okay, bye.
Jyoti, you got that email IDs from Samir?
No, no, Samir is not answering.
Anyhow, we got some. No, he has forwarded some link, right?
Yes, you have shared some links. I'm checking those only. But those are the links for just to connect through WhatsApp and the Google Meet itself. No other links.
Allocation
And
or
OS, the first class of OS, that is file system implementation and file system interface.
okay,
Uh, have received those only. Not other
okay.
than that. I have texted to madam just now. So once she ping me, I'll text in the group also. Okay.
Yeah, yeah, yeah. That is C class of Sukanya madam classes. He
Uh,
was about to send a drive, right?
yes, yes.
So once we get all those things, right? Just instead of that, we can post in group only.
Sure, sure. Definitely. Once I receive the data, I'll post it in the group.
Yeah, yeah. Because see, if we don't refer that, no, we'll not able to understand tomorrow class.
Yes,
Okay, as soon as
I
suppose
will.
just ping her or just number is there. No, her number is there already.
Yes, I'm having her number.
Yeah, yeah.
I'll
Yeah,
ping
because
her, and once I get the information from her, I'll post it in the group.
yes, yes. Mentioning that C class day two like that, no link. So that
Sure,
will be handy everywhere. So no
sure,
one will get confused. Okay.
sure.
Okay. Thank you very much.
Thank you. Bye.